Hey y'all, in this video we're going to go over the notes on electricity, or at least the first set of notes. So starting off, the definition of electrostatics is the study of electrical charges that can be collected and held in one place. When we're talking about electric charge, we're talking about either positive charges or negative charges. Objects that have zero total charge are said to be electrically neutral, but then they could have a buildup of positive charges or a buildup of negative charges, or have a neutral charge, right? So when we're talking about electrical charge, a coulomb is a large amount of electrical charge. For instance, a powerful lightning bolt can deliver about 20 to 30 coulombs of charge. So 1 coulomb is an awful lot of charge. All right. Electrical charge is conserved, so it's the total electric charge in the universe is constant. So you're not creating or destroying electric charge; it's transferred from one object to another, similar to our laws of conservation that we've talked about previously in the course. All right. For transferring charge, there's a few different ways you can do this. One way is by conduction, which is the act of placing a charge on a neutral body by touching it with another charged body. So if you like take a balloon and rub it against your hair, you're physically touching your hair with it and you're building up that charge so then your hair stands up, right? Induction is the act of placing a charge near a neutral object and causing the neutral object to become charged. So in this case, you're just holding it near it and not actually making contact. So if you happen to have a balloon, blow one up, rub it against your hair so it builds up charge, and then in a sink, make a small stream of water come out, like really narrow, like the width of like a pencil, and then hold that balloon near that stream of water, and you can watch the water bend. It's kind of neat. But know the main difference between these two: conduction is when it's touching, induction is when it's nearby. Right? So moving electrical charge in a circuit or through other materials, there's two categories for this. There's insulators, which you've probably heard of before, are materials where electrical charge does not move freely through it. For instance, rubber and plastic are going to be insulators. And then there's conductors, where your electrical charge pretty much does flow freely through it. It may not be perfect, but most metals are going to fall in this category. So depending on what you want to happen depends on what kind of material you want to use. For instance, with like your phone charger, the inside wire is going to be made of metal, but it's going to be coated in rubber to protect you from getting electrocuted when you plug in your phone. So there's times you're going to want one or the other depending on what you're doing. All right, moving on to electric fields. This is the region around an object in which a charged object experiences a force because of its charge. And we use arrows to represent the direction of the electric field, and it'll point towards the negative charge. So here in this diagram on the left, we have two negative charges, and they're going to repel each other away. And so the electric charge around this one is going to point towards each of them, and they are going to repel. Versus if we have a positive and negative charge, they're going to be attracted to one another. So the arrows are going to go towards that negative charge, right? But this is three-dimensional. It's not like a flat like picture. It is all the way surrounding it, like an atmosphere around the charge. Right. Moving on to electric force, the charges exert a force on each other over a certain distance. The force is stronger when they're closer together. Just like if you were to hold two magnets close together, you're going to feel that force is much stronger when they're close together. Like charges are going to repel, opposites attract. I kind of mentioned that on the last slide. But to figure out the electric force, we can use an equation called Coulomb's law to find the force between the two charges. So that formula is here. It's very similar to a formula we've already done in unit on our forces unit. But this is Coulomb's law. It's K is our constant, and that's going to be 9 times 10 to the 9th newtons times a meter squared per coulomb squared. And it's a constant, so you'll always plug in that 9 times to the 9th there, times the coulombs of each of our charges divided by the radius squared, or the distance between the two charges. So if we have this blue charge and this red one, that's the distance between the two of them. All right, so let's go through an example of this. So Alice rubs 2 latex balloons against her hair, causes the balloons to become charged negatively with 2 times 10 to the negative 6 coulombs and 3 times 10 to the negative 6 coulombs. She holds them a distance of 0.7 meters apart, and we want to find the electric force between the two balloons. So we're going to take our formula, we're going to plug in that constant of 9 times 10 to the 9th, then times by both of the charges. It doesn't matter which charge goes first, the 2 or the 3, it doesn't matter. And then divide that by the radius or the distance between the two squared. And do make sure you square. A common mistake I see is students forgetting to square it. Right. So I plugged this in separately. The top half equaled 0.054, and then when I simplified the bottom half, I got 0.49. You could type all of that in the calculator at once if you chose to, but you should get an answer of 0.11 newtons. It is newtons for your unit because we are dealing with a force. Right. So again, it's mostly just making sure you're able to plug it in and type it in the calculator correctly for this. All right. All right, last thing for this video is electric potential energy. We talked about energy in a previous unit and as well as potential energy. So electric potential energy is the potential energy associated with a charged object due to its position in an electric field. We're not really going to get more into it than that. We're going to keep things pretty simple. All right, but that's it for this video. Let me know if you need any help.